Right, so today we're going to look at indices. So if we open a whiteboard, let's have a look at that. Okay, so that's out to work. Right, so indices, here is an example. So this tells us, what does this tell us? So let's look at some terminology. The 3 in this case is called the base. Oh, sorry, the 2 in this case, I mean. This is your base. So your base is 3. Base is 2. Apologies, my previous example was 3. The power here is called the index, or the it's the power or the index or the exponent. So it's 2, which is a base, to the power of 4. And what it means is 2 times 2 times 2 times 2. So it's 4 lots of 2. So we say this is 2 to the power of 4, or we could say it's 2 raised to the power of 4, or it's 2 to the 4. So there's many different ways that this is talked about. But we're going to look at some rules. So the first 3 rules, super straightforward. You'll have seen them before. It's for multiplying, dividing, and when we do things to the power. So first, let's take the most straightforward one, which is when we have, let's move this so you can see it. It's when we have 2 values which we are multiplying together. So if we have a look, we've got the pink ones, we've got x cubed, and that essentially means x times x times x. And then we've got x squared, which is x times x. So we've got 3 lots of x's, and then we've got 2 lots of x's. So altogether, we then have x to the power of 5, because we've got 5 x's. So the first law of indices is x to the power of a times x to the power of b is adding them up. So when we multiply 2 powers, we add what we call the exponents, so the bit that's to the power of. So it's super easy. This shouldn't be difficult at all. And all you see a times. You need to make sure the base is the same and you can add them up. And you usually get them in algebra, and it should be quite straightforward. So let's have a look. X to the 5 times x to the 4. We're going to do 5 plus 4, which is 9. So you'd get x to the 9. So you should be able to do these all in your head. You could have p to the 2 times p to the 3. So you're doing 2 plus 3 to give you 5. I could have q times q to the 4. Now q on its own is just q to the 1. So you've got 1 plus 4 to make it 5. And it doesn't just have to be 2 things. You could have 3, 4, 5, 6 things, and it all works the same way. So that's the first one, that's multiplying. Let's have a look at dividing powers. So what would we do? Say we had x to the 5 divided by x cubed. So let's think what x to the 5 means. It means x times x times x times x times x. So it's 5 lots of those x's. And we're dividing it by 3 lots, x times x times x. Now, if we have a look, we know that we can simplify fractions by dividing the numerator, which is the number on the top, and the denominator. So what's on the top and what's on the bottom? So what we can see is there's an x on the top, we can get rid of that and get rid of one on the bottom. Get one of those, get rid of that, get rid of that, and get rid of that. And we're left with x times x, which is x squared. And this brings us to our next rule. So let's go really slowly. So this brings us to our next rule. So we've got x to the a divided by, now remember when you have a fraction, it's just a fancy way of writing divide, x to the b, so we've got a minus b. So all you're doing is you're taking away the 2 numbers. It's that straightforward. So let's have a look at some examples. Say we had 2 to the power of 10 divided by 2 to the squared. So in this case, your A is 10 and your B is 2, and you're taking them away from each other. So 10 minus 2 is going to give you 8. So that's just 2 to the power of 8, meaning 2 times 2 times 2 times 2, and so on, 8 times. If you have x to the 10 over x cubed, then you're going to have x 10 minus 3. 10 take away 3 is 7, so you've got x to the 7. We could have x to the 15 divided by x on its own. Now remember, x on its own just means x to the power of 1. 15 take away 1 gives us 14, so we've got x to the 14. So that's the second rule. So we had our first rule, which was when we multiply, we add. Our second rule, when we divide, we take away. Now we've got our third rule, which is raising something to a power. So if we've got x cubed and we're doing it to the power of 4. So what we're doing here, it's the same as x cubed times x cubed times x cubed times x cubed. So you've got everything going up. So we're saying we've got 3 plus 3 plus 3 plus 3. So that's going to give us 12. What we've actually done is 3 times 4. So this brings us to our third rule, which is xa to the b equals xab, which all it means is you just multiply it. So if you had y cubed to the 5, it's simply 3 times 5, and that would give you 15. If you had x cubed times x to the 5, that's simply x 3 plus 5, and that would give you 8. So let's mix them up. Let's take m to the 10 to the 4, and that's going to be 10 times 4, so 40. So those are the first 3 rules, and we've mixed them up and used a few examples there. So now we're going to challenge ourselves a bit, and we've got some weird rules, and these are the 0 and negative indices. So let's have a look at the 0 indice. So anything at all to the power of 0 is always 1. So if we've got 3 to the power of 0, we're going to get 1. So you could have 1,000 to the power of 0. It's always going to be 1. So anything to the power of 0 gives you 1. If I gave you a to the power of 0, that would be 1. So that's the next really important thing. Anything at all to the power of 0 is always 1. So next rule is a fractional indice. So what I mean by that is when we have a fraction, what happens is it goes onto the bottom. So let's think about what happens. So let's see if we can have a pattern which will help you see what's going on. So let's say we take 3 cubed. Now 3 cubed is 3 times 3 times 3, so it's 27. Let's take 3 squared. 3 times 3, which is 9. Let's take 3 to the power of 1. That's just 3. How about 3 to the 0? So remember what we said, anything at all to the power of 0 is always 1. Okay? Now 3 to the minus 1. So now we're going negative. Let's see what the pattern is. What have we done here? We've divided by 3. We've divided by 3 again. We've divided by 3 again. So naturally our next step would be to divide by 3. 1 divided by 3 gives you a third. Now what if I was to divide by 3 again? That means the bottom is 1 over 9. Okay, so can you see that you've got a pattern there? And essentially your rule for the pattern is that anything to the negative, so if you have a, so let's say x to the minus a, you see the minus, you know that you've got a 1 over, and then it's just x to the a. So if the minute you see a minus, you know you've got 1 over, which essentially means that you could like flip something over. So let's take a few examples. So we said x to the minus a is 1 over x to the a. So let's get that in our head, right? So 6 to the minus 1, I've seen a minus, so I'm writing 1 over, and then it's just 6 to the 1, which is 6. 8 to the minus 2, I see a minus, so I write 1 over, and that's 8 squared, which you could write as 64 if you wanted. If you had a to the minus 4, you see a minus, so it's 1 over a to the 4. So that's your negative ones. The next step now is if we have a fraction. So this is the last type, which is a fraction. And the next bit I'm just going to do is for interest, okay? So I'm just going to show you this. Don't worry if it doesn't quite make that much sense. So if we've got x to the half, and I'm going to tell you that's the same as the square root of x. And if we wanted to prove it, we could also think about a few things. We said, well, we know if we have x to the half and we times it by itself, the rule, our number one rule for indices was that we add the powers. A half plus a half gives you 1, so we get x to the 1. In the same way that the square root of x times the square root of x would be x squared, which would just give you x as well. So we've proved that x to the half is root x. Now, how can we write that in general? So in general, x to the 1 over something, so we're going to put 1 over a, is the 8th root of that x. So by that I mean, if I had, for example, let's take something that has an exact 81 to the quarter, that's the 4th root of 81. So I take the square root of 81, which is 9, and I take the square root again, which is 3. So that's all your different types of rules of indices. So you've got in total, those 5 rules. So you've got when you multiply, you add. When you divide, you take away. When they're to the power of each other, you're multiplying. Anything to the power of 0 is always 1. When you have a minus, it's 1 over. And when you have a fraction, it's a root. So what we can end with is having a look at how this is then tested in sort of, I'd say, trickier questions. So let's take a few from some exam papers that might be sort of trickier questions. Right. So you might get something like this. You've got solve. Now this is a big jump. So this is going to like, from those very straightforward indice questions, we're now jumping to how it could be tested in a higher question. So we've got 4 to the power of x equals 2 to the power of 10. So remember we said we can't do much unless the base is the same. So the base is this number. This is a 2, this is a 4. Well, that's not that useful. So step 1, we're going to try convert everything into a power of 2. So we're going to take that 4 and we're going to change it into a 2 squared. So we've now got 2 squared to the power of x, which equals 2 to the 10. And we know our rule is when they're like this, we can multiply it. So we've got 2 times x, so we get 2x. Now, if you notice, the base is now the same. So now we can just say 2x is the same as 10. So x must be the same as 5. So that's a trickier question where you've had to take a value and make the base the same in order to answer it. So here, what we've effectively done is we've changed the base. So we do this when we need to change the base. All right, let's take something, let's take one more like this. So if we take something a bit trickier again, let's take 2 root 2 equals 2 to the power of something. And we have to work out that something. So looking at that again, you're like, what? So this doesn't really look like anything we've seen, but we know when numbers are together, it's the same as timesing them. So this is the same as 2 times the square root of 2. Okay, so we know that that's 2 times, and we said anything to the square root is to the power of a half. Now what we can do here is this is to the power of 1. When there's a time sign, it's the same as adding the powers. So we get 1 plus a half, which makes 3 over 2. So we get 2 to the 3 over 2. And now we can see that k equals 3 over 2. So that's the way it's tested as you go up and you get to the sort of higher level questions. So that's a very, very brief, very, very quick indice introduction. The bit that takes it one step further is when we start to look at surds. So we're going to break this into 2 videos. So this is indices, and I'm going to stop this and start again and have a look at surds. You don't get how it's 3 over 2. Okay, so if I have, so my rule is x to the a times x to the b is xa plus b, right? So this is my a, this is my b. So we've got 1 plus a half, which gives us 1 and a half. And if you like to convert that into a top-heavy fraction, 2 times 1 is 1. 2 times 1 is 2, plus 1 is 3. So we get 3 over 2. So that's where that power comes from. I hope that makes sense. So that's how you change the base. So the next bit of this is surds, which is, I guess, the trickier bit, but you need to understand the indices to be able to deal with the surds. So now let's have a look at surds. So what I'm going to do is clear this and let's have a look at surds. So I know, like I said, we've done this before, but unfortunately I don't think it's saved. And a few students asked for it again. So hopefully on YouTube now, everything should be saving. Right, so surds. Different types of numbers. We have what we call real numbers that are split into 2 types of numbers, rational numbers and irrational numbers. So rational numbers are numbers that you can write as a fraction. So a half, a quarter, all the whole numbers because they're 2 over 1. And we have irrational numbers, which essentially you can't write as a fraction, but they're, you know, still a type of number like pi, like any square root number. Anything like that we call irrational. Now surds, there are only 2 things that you need to know. So this is a super easy topic. For some reason it stresses everybody out, but it shouldn't. It's very, very super straightforward as long as you learn these 2 rules. So the only 2 things you need to know is that the square root of a times the square root of b is the same as the square root of ab. Now, if you remember, AB just means A times B. And the square root of A divided by the square root of B is the same as the square root of the whole of A over B. So that's the first thing that we need to know. 2 rules, nice and straightforward. Let's take a couple of examples. So if we've got root 3 times by root 2, 3 would be my A, 2 would be my B. I multiply them together. 3 times 2 gives me 6. So that's an example of the first one. And an example of the second one could be the square root of 3 divided by, it's going to be top heavy, but square root of 2 we could just write it as a square root of 3 over 2. So we can just combine it together. The same way that square root of 1 over 9, we can take the square root of the top, which is 1, and the square root of the bottom. So that's using the rule the other way around. So that's the first thing to realize. And we're going to mainly be using this rule to help us simplify surds. So to make surds simpler. So we can break up a bigger number into a smaller numbers. And in order to do that, you need to remember what your first few numbers squared are. So we know we don't need to bother about 1 squared, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So you're just sort of bearing that in mind. So you have that at the back of your head that you know that these numbers, what they are squared. So let's take square root of 8. We think of these numbers we have, 4, 9, 16, and say, does 8 go into any one of them? It does, it goes into 4. So we say this is a square root of 4, square root of 2, because that's using that rule that the square root of AB, so the root of AB, A times root B equals root AB. We should always write it like this as well. And then we say, what's the square root of 4? Well, we know that's 2. So we get 2 square root 2. So you find the largest square factor of the number. And if you put it first, it just looks nicer. So writing 2 root 2 is about like root 2 times 2, which is the same thing. It just looks nicer. So let's take a few more. Let's take root 32. So again, I'm looking at my list thinking 32. Hopefully you recognize you've got root 16, root 2. So 16 times 2 gives you 32. The square root of 16 is 4. So you get 4 root 2. If we had the square root of 27, so you'd say 9 times 3 is 27. So that's the square root of 9, the square root of 3 to give you 3 root 3. Okay, so knowing that rule makes simplifying surds super easy. Now, generally, when they ask you to simplify them in an exam, it will be something that goes into those factors. So let's take something that has a number in front. So say we had 5 root 75. So we've got the 5 in front. We sort of almost don't worry about the square root of 75. So we're like the 5. We're looking at just the square root of 75. So we're saying, all right, we've got the 5 here. We don't need to split that up. 75 is the same as 25 times 3. So 25 times 3. So root 25, root 3. The square root of 25 will be 5. So we're going to have 5 times by 5 root 3. So we get 25 root 3. I think I've got a question. Oh no, I'm just making someone sleepy. All right, well, sorry. Unfortunately, this isn't exciting. It's maths. You kind of got to get through it. I haven't got a way to make surds any more exciting than this. Okay, so if you got a number in front, you treat it in exactly the same way. So when we're multiplying surds, we have to be very careful whether we've got a number or it's a surd. So just don't get caught out. So if you had, I don't know, root 3 times root 5, like we said, that was one of the straightforward rules. 3 times 5 is 15. However, if I had 2 root 5, 2 times root 5, I can't do anything with that because the 2's not in the square root. So it is just 2 root 5. Okay. What about if I have a mixture of like non-surdy things and surdy things all together to multiply? So if I had, for example, 3 root 2 times 3 root 3, the thing to do first is to multiply together the non-surdy stuff. So if I have a look, I've got a 3 and a 3 here. I multiply that separately. So 3 times 3 gives me 9. And then I do 2 times 3, which is 6, and that goes underneath the square root sign. So that's multiplying surds and simplifying surds. Next step, adding surds. So now we can only add surds if they're the same. So think about it like this. If we have root 2 plus root 2. Well, what we've got here, I've got one lot of root 2 and another lot of root 2. So all together, I add them together and I've got 2 lots of root 2's. So I've got 2 root 2. So you've got one lot and another lot, so you've got 2 lots of root 2's, but they have to be the same. You can't add, if I had root 2 plus root 3, they're separate things. That's still root 2 plus root 3, because it's not adding the same things together, okay? So I could do, so if I had 7 lots of root 7's and plus 2 lots of root 7's, it's just 9 lots of root 7's. Now, exactly like algebra, where you collect like terms, so you pull the x's together, you pull the y's together, and so on. So now let's think about if they're not the same and they're telling you to add them or simplify it, that means there must be a way to simplify one of the other surds. By that I mean, if you've got 3 root 12 plus root 27, you're going to say, okay, well, as it stands, there's nothing similar about them. But let me think about it. 12 is the same as 4 times 3, and 4 is an exact surd, and 27 is 9 times 3. So if I put that all together, I've got 3 root 4 root 3 plus root 9 root 3. So this bit matches up with that, and the root 4 root 3 matches up with a 12. Now I know root 4 is 2. 2 times 3 is 6. So I get 6 lots of root 3, and root 9 is 3, so 3 lots of root 3. And now because it's the same, I can add them up. All right, so if you get something in an exam where it's worth 2 or 3 marks and it doesn't look obvious that you can add it, there must be a way to simplify it, and you're getting more marks in order to simplify it. So we've done multiplying, we've done adding. Now let's have a look at brackets and opening out brackets. So let's take one bracket to start with. So a nice, hopefully more straightforward. So if we've got a root 2 on the outside, we know from what we've learned previously is that any number on the outside means everything inside is multiplied. So what if you had 78 to the power, oh, okay, this must be from before. Anything to the power of 0 is always 1. So by anything to the inside. So root 2 times 3 is going to give you 3 root 2, because you're taking the root 2 and multiplying by the 3. That's that first arrow. And then you've got root 2 times by root 2. So if you think about it, that's the same as 2 times 2, which is 4. The square root of 4 is 2. And that's another thing just to bear in mind. Root A times root A is A. Root whatever, root 12 times root 12 is going to be 12. You're always going to get the number underneath. So root 2 times root 2 is going to give you 2. So here we've got 3 root 2 plus 2. What if let's take another one just to make sure that's made sense. Let's say root 3, and inside we could have 6 plus root 3. So in exactly the same way, we've got root 3 times 6, which is going to give you 6 lots of root 3, plus, and then we've got root 3 times root 3. And remember, anything times by itself will just give you 3, because effectively root 3 times root 3 would be root 3 times 3, which is root 9, which we know is 3. But you always get the number underneath. Okay, so now let's look at double brackets. So regardless of the method you use, whether you use FOIL, you put them in it doesn't matter. So if we have root, let's do one where it's a difference of 2 squares, but we don't necessarily need to. If you recognize that as a difference of 2 squares, well done. So that's root 2 plus 1 multiplied by root 2 minus 1. So you're going to get root 2 times root 2, which gives you 2. Root 2 times minus 1, which is going to give you minus root 2. Then you've got 1 times root 2 plus root 2. And root 2, so we've done that. Root 2 times root 2. Kind of did this in a weird order. So let's get rid of that last one. So root 2 times root 2, which is, we've done that, and 1 times minus 1. So minus 1, there we go. So we've got 2 minus 1, which gives you 1, and these two cancel each other out. So whenever you times, that was a bit messy, I'll do another one just now. Whenever you times something by its like inverse, when it's a plus and it becomes a minus, you should always get rid of the roots. So let me take another one. Let's say root 7 plus 3 multiplied by root 7 minus 3. Okay. So we're going to have root 7 times root 7, which is going to give us 7. We're going to have root 7 times minus 3, which is going to give us minus 3 lots of root 7. We're going to have, so I've done this times this, this times this, so we've got this times this, 3 times root 7 to give us 3 root 7, and then we've got 3 times minus 3 to give us minus 9. And what you notice again is that these cancel, and you're left with 7 minus 9, which is minus 2. So whenever you have something like that, you cancel it out. Let's take something that doesn't necessarily cancel out. So let's take root 8 plus 3 multiplied by root 2 plus 5. Okay, now from what we did previously, we know that root 8 simplifies, but I wouldn't worry about simplifying it inside the bracket. You're just going to confuse it. So we're going to do root 8 times by root 2. So that's my first thing I'm going to do. And that's going to give me the square root of 16. Then I'm going to take root 8 and I'm going to multiply it by 5. So that's going to give me 5 root 8. And then I've got 3 times root 2 to give me 3 root 2. So I've got root 16, 5 root 8, 3 root 2. And what have I got left? Then all I've got left is 3 times 5 to give me 3 times 5 to give me 15. So now looking at that, is there any way to simplify that? Well, we can see that root 16 we know is an exact root, it's 4. Root 8 we can split up like we did earlier into root 4 and root 2 plus 3 root 2 plus 15. Okay, so now let's combine the 4 and the 15. We're going to get 19. Root 4 is 2 times by 5 gives us 10. I've tried to do this step by step. And so then you get 19 plus 13 root 2, and that would be your final answer. Let's take something that's squared, so multiplied by itself. So let's take root 5 minus 2 all squared. So what does that mean? If something is all squared, it means I'm multiplying it by itself. So I've got root 5 minus 2 multiplied by root 5 minus 2. So I'm going to have, let's do it like this. So like that. So we're going to multiply everything out. When I multiply it all out, I get root 5 times root 5, which is 5, minus 2 root 5, minus another 2 root 5, and then a minus and a minus make a plus, so plus 4. Put all the numbers together, and put all the root 5s together. So that's if you have a bracket. And how that's normally tested is sometimes they give you an area or they give you a shape and they say work out the area of this, and one side is actually given as a surd. Now the last sort of section of this is looking at rationalizing the denominator. Now all rationalizing means is we don't want the surd on the bottom. We don't like it on the bottom of an equation. So this is where having the square root and knowing that if I multiply it by itself, I'm going to get rid of the square root becomes really, really super useful. So this is where I know that root 3 times root 3 is 3. And so what I want to say is I don't want that square root ever on the denominator. So for example, if I had 1 over root 2, I want to rewrite that. Now I know if I multiply everything by 1, it stays the same. So root 2 over root 2, which gives me 1 times root 2 will give me root 2. Root 2 times root 2 on the denominator I know gives me 2. And now I have something without a root on the bottom. This is exactly the same as this. It's just written differently. So I can that's called rationalizing the denominator. And there are 2 reasons why we want to do this. It makes us easy to do expressions, but also it's a bit of an aesthetic thing. It just looks nicer. It's nicer to divide something whole. But in maths, we use it later on, and it makes other calculations a lot easier. So let's take a few. Let's do a few. So we've got 6 over root 3. I'm going to multiply the top and bottom by root 3 because that's effectively multiplied by 1. So it doesn't change anything. 6 times root 3 is just 6 root 3. Root 3 times root 3 is 3. And now I can do 6 divided by 3 to give me 2, and I've simplified it without a square root on the bottom. So let me take, say something, let's find one from an exam paper. Here we go. So they've got 8 over root 10. So again, I'm going to multiply the top and bottom by root 10 over root 10. So we get 8 root 10 on the top. Root 10 times root 10 is 10. And we can cancel that down, divide top and bottom by 2. So we get 4 root 10 over 5. And that takes you all the way to the level 9 questions. And then to take it, I guess I could take it one step further, but this is more for, this will more come up in further maths, GCSE. So this is the I'm just going to do one example, and this is when you have a more complex denominator. So, so if I have, for example, root 2 plus 1. So do you remember that rule where we had, if we change the sign, it gets rid of all the surds? So if I was to multiply that, I have to multiply it by the same thing, not to change it. But what I've done is change the plus into a minus. And now if I multiply that, I've got 1 times root 2 minus 1 on the top. And on the bottom, I end up with root 2 times root 2, which is 2. Root 2 times minus 1, minus root 2, plus root 2, minus 1. And these will always cancel out. So you end up with root 2 minus 1 over 1, which is just root 2 minus 1. And that's using the difference of 2 squares. So when you've got something in this form, you get a squared minus b squared. Okay, so I hope that was useful. I think I saw a question earlier about uploading A-level math stuff. Yes, I've put up the log stuff that I did yesterday. The math lessons are currently running quite late. They're running from 10 to 10, they're starting at 10 to 10:30, 10:40 in the evening, because of a lot of my students are like fasting and doing Ramadan. and wanted to do them late in the evening. So A-level lessons are running late in the evening. I unfortunately can't do a science lesson today, but hopefully for those of you that, I know we've done this lesson before, but it didn't save, it's now saved on YouTube as well. And I hope that was useful, and I will see some of you tomorrow.